first one being the search for ultralight axions. So you can think of these in the regime of less than a eV, and then after that it'll be the heavy axion search with similar machinery as the ultralight one, except now we're in the mass regime of MeV or so. And I will finish it off with future observations with some hopeful future observation instruments that we're trying to push with people at Berkeley. Okay, so axions and supernovae. So I know there's a lot of people in the crowd who are familiar with axions, so I didn't put too much into the introductory, but it's a hypothetical pseudoscalar. It has a wide range of possible masses, as you can see from these two limit plots that I pasted down here. I pasted these two specifically because these are kind of the ranges that I would be talking about today. So I would like you to keep these two in mind. And there's a broader category of axion-like particles that we refer to more commonly, where it doesn't necessarily solve the strong CP problem, but it has similar properties as the axion, where it couples to photons in this term shown on the upper right. So I'm mostly going to be talking about ALPS today, but there are going to be specific portions in the ultralight axion search where there will be QCD axions that I'll be discussing. But I will be specific. I want to say that when I say axions, I mean generally ALPS, not QCD axions. And when I am referring to QCD axions, I will say the word QCD axions. So just want to make that clear before I move on.
Thank you.
Yeah, no problem. Okay, so sources of axions for searches in astrophysics. There are multiple sources that I just kind of threw up on here. With, if you consider axions as dark matter, you can consider the dark matter halo in our Milky Way. Like we have all these direct searches of axion dark matter experiments like ADMX, like I just quoted. There's also, you could maybe consider the source of axions coming from axion strings, like emanating from the strings. I'm not an expert on these two, but so I won't touch on these. But for this talk, I'm going to specifically talk about axion production in supernovae, because these are very extreme conditions that are created in the core of the supernova that makes axion production much more efficient than any of the other sources that I've considered here. All right, so core collapse supernovae, just a quick overview. What happens at the end stages of the life of a heavy star is it accumulates iron in its core, and this iron no longer produces energy through fusion. Oh, oops. So it starts building it. It can no longer support the gravitational pressure with fusion in its core. So it collapses, produces this proto-neutron star core at the center that's very hot and dense. And it's known to cool through the emission of neutrinos. And we've observed this neutrino burst through like various neutrino observatories, specifically for the famous supernova 1987A, which I will be referring to a lot for the ultralight search. But also, we can consider the axion production in this hot, dense core at its initial stages as well. So the ingredients for the search that I'll be talking about today in wide, I guess, both for ultralight and heavy axions, is we want to figure out the axion emission spectrum calculated with the interaction terms in the Lagrangian of, oh yeah, go ahead.
Are neutrinos the only direct evidence we have of these proto-neutron stars? What is that?
Sorry, what do you...
How model dependent is our knowledge of like their temperature and so on?
Oh, yeah, I believe it's mostly the neutrinos, because in the initial stages, if I go back, like when this core forms, which is like a couple seconds after the initial collapse, there's no photons escaping here. It's just mostly the very weakly interacting particles that come out, and it's mostly the neutrinos that we...
And we can directly probe the temperature of the...
No, yeah. But what we do, I guess I'll mention this later on, but there are simulations where people have done to understand the core properties at the early stages of the core collapse, and their neutrino emission prediction from simulations match pretty well with what we have observed with supernova 1987A. So that's why we're like, okay, this is probably the best we can do for now. And also there's, I guess it's sort of a tangent, but there's also like work that people do on trying to set constraints on BSM where you can't have too much emission in these BSM particles, because then it would mess up what we would see in neutrinos.
Sure.
Yeah, so those are kind of the main ideas. All right, so the key ingredients for the search that I'll be talking about today, like I mentioned first, we have the emission spectrum that we want to calculate with the interaction terms and the simulations of the collapse. So that creates the axions. And in order to detect these, we want to look at its conversion or decay to gamma ray photons, and that's where we'll be calculating different, either the conversion or the decay rate of axion to photons. Finally, the last would be we'd observe these with gamma ray telescopes and work on data analysis to see if we can either see them or, if not, set constraints on the coupling of photons to axions to photons. So this is the main idea. And to give you an overview of, I guess, what to come, specifically for the ultralight axions of masses less than eV, we'll be considering the conversion to photons in magnetic fields. And for heavy axions of mass of order MeV, these have shorter lifetimes, so now they decay to photons. I guess also one thing I want to emphasize here is, before I move on to the details of the work, that these axions aren't necessarily dark matter. They're very light or very heavy. So like for the ultralights, these may be too light to be dark matter. And also for heavy axions, these are too heavy that they're just not long-lived enough to be dark matter. So I want you to consider that this is not necessarily dark matter in the talk setting.
Not necessarily, or with some model building you could.
Yeah, I guess with some model building you could, but specifically for heavy axions, there's no way. It's just the lifetime's too short, so you'd never be able to get them as dark matter.
Sorry, what was the problem with the ultralight being dark matter again?
Oh, I'm just saying that for the ones that I'm considering, they're just too light to be dark matter.
From
QCD, axion, and dark matter.
Like they're above the yellow band, or like.
Oh, I'm not. Yeah, they're above the yellow band. Yes.
Yeah, they're like way below EV, or.
Oh yeah, way below. Like I will be going down to ranges of 10 to the minus 12. So like ultra.
Misalignment's overproducing?
I think.
Oh yeah, well I guess.
Underproducing.
Right, but then you're
But
like
you're
kinetic
going to hit the band at some point, right?
Yeah, at some point with QCD axions or sensitivities that I'll be showing, but not necessarily with the limits that I show. There won't be any dark matter.
Okay.
Or like it doesn't have to be dark matter. Like
Yeah.
your dark matter could be some other particle, but we would still be able to search axions with this method.
Sure. If it's underproducing, that seems easier.
Yeah.
There are many ways to overcome it.
Right. If
But
it's
yeah, a 10 minus 12 EV scalar could be dark matter.
Yeah, of course.
Oh
But
yeah.
You're not
like-
using it. You're not using that fact.
Yeah.
Yeah.
Sorry, I should have worded that better, but yes, it's the fact that this doesn't have to be. We're not searching for this in the context of dark matter. Okay, so ultralight axions. I realize that I sometimes do hyphens and not hyphens, but okay. So the couplings we consider. So we want to start off with the first ingredient that I mentioned here, where we want to calculate the axion emission spectrum. And so typically when people talk about ALP production in supernovae, people consider this coupling to photons, a GA-FF dual, right? But what I'm presenting in this work is that when you consider its coupling in UV to give you that photon coupling, it actually induces a nucleon coupling in the IR through like loops in your diagram. So you start off with this UV. Sorry, I'm just going to move this real quick. And that this UV term leads you to the terms in the IR where you can reinterpret these coupling constants in terms of the CW and CB coefficients that I've shown in our UV scale. So in this work, we considered a UV completion where CW equals CB, but you can play around with it to get with whatever ratio you want and plug it in to try to reinterpret the results. So basically what this lets us do is if we have a coupling to nucleons, we can reinterpret that into J gamma gamma so that we can put it all in a single plot of J gamma gamma versus MA. Sweet. And so with these terms, we use the production mechanisms shown in these four main diagrams with the usual Primakov production with its coupling to photons, and then the nucleon bremsstrahlung where it brems off of the nucleon in the protoneutron star core. And then finally, the more controversial production mechanism called the pion conversion because people aren't quite sure of what the density of pions would be like in the proneutron star core. So it's more controversial, but we're considering it in the work, although the analysis won't actually be affected by how we consider this pion conversion rate.
Sorry, go ahead.
I have a question about the
Yeah.
previous slide.
Previous
may-
slide,
may-
yeah.
too.
Okay, being that no, previous to that.
Oh.
So
okay.
I'm familiar with, okay, so you have a coupling to W's and hypercharge, so I can see you couple to the photon.
Mhm.
Usually that derivative term to nucleons, I'm familiar with, if you couple to gluons or quarks, right? Because because of axion pion mixing and the pion couples to photons, you get that one. You get corrections to both. But okay, so let's say you only couple to W's and B's. What's the diagram that gives the derivative coupling to nucleons? How do I see that?
I can't
It's
remember.
a
the
non-hadronic
exact-
coupling, right? So
Sorry?
Is that GAN loop suppressed or?
Yeah.
The
It's
coefficients
okay.
were small minutes. Actually, I have a correlated
Yeah.
question on the
Yeah.
next line,
oh.
which is just like out of curiosity, how uncertain are the coefficients here? Like a,
Oh, what do you mean the
so
GAN?
it's
or
5.6
GAP?
times, like those coefficients.
I actually don't remember
Yeah,
the
I just wonder,
uncertainty on the.
because that will affect the interpretation of the bounds if
Right.
those were very uncertain or not. I'm just
Yeah.
ignorant.
Oh, but so
That's a
that's a
good point.
one loop perturbative.
Yeah.
Yeah,
okay.
so it should
Yeah,
be
yeah.
pretty solid, right?
Yeah. No, then you know. Sorry, I was being slow. Because normally, I mean, those are the minimal couplings that have to be present.
Mhm.
Likely, if for the QCD axion, those coefficients are much bigger.
Oh,
right?
yeah,
They're
yeah,
Order
yeah.
unity. Yeah.
Right,
so
right.
This is just loop suppressed.
Yeah,
Okay.
exactly. So you will actually see in the final axion emission spectrum where I show DNA over DE, it's much higher in the axion emission from nucleon bremsstrahlung for the cases where you have QCD axion, the QCD case.
Okay.
So yeah, these are okay, so sorry. Before I jump to the final production, what we also need in addition to these production mechanisms is we need to know what's happening in the core of the proneutron star that's produced in the immediate seconds after the core collapse. And so for this, we refer to this Garchian core collapse supernova archive. So we just take the data that is available of people who have worked on the simulations, specifically for the 3 cases stated here, the FHO 18.6, 18.8, and 20.0. The numbers refer to the different progenitor masses, and because of the different progenitor masses, you have the different resulting neutron star remnant mass. And what I want to state here is that although these, well, I guess also it shows in the next slide, but we choose our fiducial simulation based on the estimates on the remnant mass for specifically supernova 1987A. Yeah,
But
so,
what-
which
what
is like the
what's in this range?
18.6. Yeah.
Oh, okay. 18.6.
Yeah.
How uncertain is that?
Sorry?
How uncertain is that? Like
Is the mass of
progenitor
the-
mass estimation
Oh,
of things? Is it like we know it's 18.6
No,
and not
there's
18.8?
a pretty big uncertainty, but I guess we choose fiducially this one right here, where it's the middle of the two, but it doesn't really vary that much by its remnant mass. And then also additionally, it's the fact that this mass range from when we were talking to simulation, the people who worked on the simulation, is that it covers the range of neutron star remnant masses that they expect from the core collapse.
Right.
Like this is like the lower and this is the upper that they suspect.
I forget the status, but they never found the neutron star itself, right?
Oh no, they didn't. But they, like, how do I put this?
There's evidence for a compact
They have
object.
with
Oh
James
wait,
Webb
you mean for
pretty
supernova
strong.
1987A?
Yeah.
Oh yeah. They
3
have
astrophysical signals.
yeah. There are
There's like
some evidence.
Because there were like a while ago there was this kind of polemical stuff like Fear Bloom, for
Yeah,
example.
you
Like
get around
we don't
it.
really know how it exploded. That maybe it exploded in a different way, where you don't get a
Oh.
neutron star, right? And then
No,
the bounds would be very different.
Sorry, Kfir was doubting type 1A supernovae specifically, I think.
Oh.
This is core collapse supernova.
This type
right?
two.
No, I'm pretty sure it was.
I thought he was applying it to
Yeah.
the 1970
Yeah.
bounds
Oh, really?
specifically.
Okay.
Yeah.
Oh.
So I thought they were saying maybe this exploded in a different way where the bound doesn't apply.
Yeah, he was saying,
oh,
like,
I was not familiar.
If he had some other explosion mechanism
Yeah.
that led to a black hole, and then you don't get any of these, at least the light.
But then,
axion
which makes that
constraints.
compact object measurements really interesting if one
Yeah,
takes seriously
but
what they were saying.
They claim to have seen like a point source with James Webb at the expected location that's heating the medium.
But if it's
But-
3 astro sigma,
Yeah.
Yeah.
It's unclear. There's some evidence of a compact object heating the gas around it in that general vicinity.
Yeah.
Also, wasn't there some problem with these 1D simulations about even getting supernovae to explode?
Yeah, that's right. I think they just make it explode. Like, there's no simulation that actually evolves that naturally undergoes like core collapse and explosion. It's just like, I think for the specific one, this just started with the core collapse.
Okay.
that,
Yeah,
that
it
was part of
doesn't-
the ideology that fear people
I
with,
see.
with
Yeah.
Yeah,
I wonder,
that's true.
I just didn't follow, like, is the status of that, do people take seriously this fear thing?
Well, I think, I mean, in 3D they make them explode now, and part of the problem was that I think like this group, their 3D simulations explode. I think they were the first ones to do it. And part of the problem was in 1D it just takes longer to explode, and they weren't simulating far enough out, if I remember correctly. So it would simulate like, it would explode a couple seconds later than they would simulate.
Okay.
I think.
But now it's okay in 3D.
I think in 3D it seems like the
Yeah, I think I
the
heard something about being able to get it to work.
Wait, does that have to do with the asphericities or?
The asphericity helps it explode, so in 3D it explodes earlier, I believe.
But it's not a condition because I thought the simulations they said spherically symmetric.
Yeah, the ones that I'm using here are, but they've done a multiple different simulations. Like this image, I guess, is one
Yeah.
that I just took from their website. But yeah.
I think groups after, there's like a group in Tennessee that runs these as well, and if you run the 1D simulations for longer than they have been, then they explode in 1D. But the asphericity helps you explode, so in 3D they explode earlier, and that's this is what I remember from my talk from like a year ago. Anyway.
Okay.
I had a question about this. So why is the 18.6 progenitor mass the middle neutron star mass?
Seems
Seems like a very big neutron, like, range of possible neutron star masses for such a small range of progenitor masses.
that I'm not sure, but this was kind of the range of this 3 simulations that they gave us, where it was like 18.6 is the one that's probably closest to their expertise were saying that would be closest to the remnant from supernova 1987A, and then the 2 other ranges were the ones that would kind of envelope the range of remnants that you would get. I don't know if they have other.
Are they varying any other parameters than just the mass? Or is it just
I believe it's just the mass, of the progenitor. But I don't know why the remnants are so different between the 2. Like, I would naively have expected the ranges to go like 18.8 is the middle one, based on the remnant, the progenitor mass hierarchy, but this is what we were working with.
Do they include pions or anything like that?
Yeah, I believe they do. I think there is okay, this is something I didn't put in my slides, but there's like a question of how you deal with pion condensates in these situations, because there is a part of there can be regions in the proto-neutron star, like the initial stages where it's really hot and dense, where there could be temperatures and densities high enough to form pion condensates, but we're not sure how that actually contributes to anything like the axion emission signals and things like that, so we kind of ignore it for now. I think Claudio and Josh Benabu are working with Ben and Hitoshi. I'm not sure. Don't quote me on the collaborations efforts going on
There's a
to
question
understand
of
this.
time scales here, right? Because
Yeah.
the proto-neutron star is like some like semi-stable thing for, I don't know, it's like a few days or something?
Well, I mean, in our work, we only consider the first 10 seconds.
Okay.
Since
So
the
maybe order
collapse,
seconds
yeah.
then. And you need to have enough time for like a pion condensate to really like when I think of a condensate as some like stable configuration of pions that has some like solitonic structure. I'm just curious about the time scales for all these processes.
Yeah,
They
I'm
have
not
to be very
sure.
fast, right?
Yeah, it's still, I think, very much up in the air. People aren't sure how to deal with those at the moment. I think Claudio and Josh both did a very extensive literature search on to see if there were any work done in this aspect, and they haven't found. I don't think they were able to get any answers so far. Yeah. But yeah, it's kind of like the steps, I guess, future steps to be made to understand better what the axion emission spectrum would be. Because you could get potentially enhancements from that, maybe, but also I don't know if it would necessarily diminish your signal. But yeah.
Yeah, we should probably.
Sorry. We should continue. Okay, so these are the three temperature profile within the PNS at different times, as shown here, like the first 10 seconds of the core collapse, and like I mentioned, we're using the leftmost as our fiducial, but I will also show how the limits vary with different simulations later. Okay, so with all of that put together, we get this plot of the axion emission spectrum, where you can see that the black lines are the ones that show the emission spectrum with ALPS, and like it was mentioned earlier, when we consider QCD KSVZ couplings, we get a larger emission with the production mechanisms through nucleon Bremsstrahlung and then the pion conversion because of their direct coupling to quarks. So yeah, it's not shown because it overlaps, the lines overlap, but the Primakov doesn't change, right? Because between the two, because whether it's QCD or ALP, they still have the same. We're quantifying this by the Ga gamma gamma coupling of 10 to the minus 12 in this GV, so those stay the same between the two regardless. Okay,
Those
so
large numbers on the y-axis.
Sorry?
Can you give me a feeling if 10 to the 50 is a large number?
okay.
How fast does it cut off?
It does cut off quite quickly towards like the late stages of the simulation that we consider. I think it goes from like 10 to the 55 to like 10 to the 40, I want to say. I'm just remembering these numbers off the top of my head, so don't quote me on this. But yeah, it drops off pretty quickly, but also you have to consider the fact that these are emitted very far away. So even if there's like a high flux, high number of emissions, they're just completely diminished when you consider the flux on Earth. Yeah.
This is kind of an evil question to ask, but like, how much solid angle is the Earth as a fraction of the sky?
Ooh.
It's very tiny, right? Compared to this number.
What's the distance to?
Yeah, what's the distance?
It's what is it? 400 kiloparsecs.
Oh no, this is 50. Yeah. But
It's very small.
I can't give you an estimate right off the top of my head, unfortunately.
All
But
astronomy plots should have these units, by the way. We love it for that.
There are no astronomy plots with these.
They should all.
They should.
This should. Yeah.
It's not there. I love this.
I want it always this.
yeah, but also I guess in addition to this, you have the distance, but also you lose out because of the conversion to photons that has to happen, which is like 10 to the minus 6 or so of axion converting to photons. So these numbers may look really large, but in the end, what we observe ends up being quite small. So yeah. Anyways, so that's got us to this getting the axion emission spectrum. Now we want to consider how we observe these, and we are now for the ultralight considering their conversion in magnetic fields. Previously, what people have done to calculate the limits is they considered the photon conversion in galactic magnetic fields. So these are like micro Gauss strength fields, and this was what gave the limit shown here in this plot that I've highlighted. But what are some other magnetic field sources that maybe we can consider? So this is what led to this specific paper, where we consider the magnetic field of the progenitor. So what the schematic is that what happens is in the first couple seconds of the core collapse, the axions escape, they're ultralight, so they escape in relativistic speeds. the outer envelope of the progenitor is still not disturbed. And so it escapes fast enough that it encounters the pristine magnetic field of the progenitor. And these magnetic fields are of order kilogauss, so there's much stronger magnetic fields. So this could potentially give you better sensitivity in the axion to photon conversion. Higher axion to photon conversion probabilities. So that's what prompted this.
Is that well known?
Sorry, what do you mean?
A kilogauss?
No.
Okay.
No, for sure not. That's why we consider a wide range of possibilities for the magnetic field.
Yeah, that's exactly if you see a signal, great, but can you really set a conservative bound?
No, but I think
on
also
axions?
if you observe okay, maybe you can't set a conservative bound, but I think there is also a range of possible magnetic field strengths that if you go below, it would become, how do I put this, unphysical for a progenitor that we're considering for supernova 1987A.
Yeah, I guess that's
So-
a way of rephrasing my question. Can one with certainty quote a lower bound on the size of the magnetic, 0.1
Yeah,
kilogauss, at 2 sigma?
I mean, I'm referring to the the experts on the blue supergiants, I guess specifically for supernova 1987A, that the range of blue supergiants field strengths are 100 gauss to 10 kilogauss. So yeah, of course, for limits that we present in this paper, we want to be conservative because we don't know what the exact magnetic field strengths are. So we use this 100 gauss to be as most conservative as possible. Yeah.
How do they do xenon spectroscopy?
Yeah, okay, so
nearby?
for current blue supergiants, yes, that's what they do. But for supernova 1987A, since they have to do this retroactively in some sense, because they have to look at the data that was there before. Well, okay, they have to somehow infer the magnetic field of the progenitor for the supernova 1987A. And so what they do is they do this I read through the paper, didn't quite fully understand it because I'm not an expert, but they do some kind of study in the medium outside the shock wave of the supernova to see if they can infer the magnetic field strength at the time that this was still a progenitor. But they estimate 1 kilogauss, which could be too optimistic, which is why we use 100 gauss for our fiducial limits. But yes, there are uncertainties. But if we were to observe something go off now, I think we'd have enough data to know what its magnetic field strengths would be. Yeah, I mean, we have the tools to know. Yeah. So. Yeah, so this was located 50 kiloparsecs away. And like I mentioned, the typical blue supergiant strengths, magnetic field strengths range from 100 gauss to 10 kilogauss. We obviously want to be conservative with our limits, so we take 100 gauss for our final limit plot. But I'm going to walk through a quick rough estimate of the conversion because there is an issue that when you consider this simple conversion probability equation of J gamma gamma squared, B squared, L squared, we do lose out for the progenitor magnetic field in L because the length scale that we consider for blue supergiants are much shorter than the length scale of galactic magnetic fields. So we went through this rough estimate at the initial stages of when we were thinking, oh wait, is this going to be reasonable or not? And it actually turns out that we win on the magnetic field strength, but we lose on the distance scale, which somehow seems to, specifically with these examples, we get something very comparable. I know that, I understand that this 1 kiloparsec is very small for a galactic scale, but also it's still very comparable even though if you put in let's say 20 kiloparsecs or so. So it seems like although the magnetic field strength is stronger for a blue supergiant, the conversion rates conversion probabilities are comparable. So what do we really win on here? And that is what I actually just spoiled, is that we actually get higher mass sensitivities for the conversion of axion to photons. So this is kind of like a schematic to show you why this is the case. Typically when you look at these limit plots, they have a plateau and then it turns to losing sensitivities. And that threshold of MA can be approximated with this expression here, where it comes from the fact that the dispersion relation of the axion and the photon is different. So if the difference is if the state delta phi is too large, then you don't get an efficient enough conversion. And actually, because the length scale is so short in the blue supergiant, we're able to get better conversion for higher mass axions. So this is kind of like a quick estimate of where you can get this threshold of MA that you get for this plateau region in your limit. And so if we plug these numbers in, we see that the plateau ends for a galactic magnetic field at around 10 to the minus 9 eV. But with stellar magnetic field, we're now able to extend that up to 10 to the minus 5 or so. So your sensitivity drops out in a much higher mass compared to when you're considering a galactic magnetic field. Okay? So now we look for these signals in data. So what we did was we took this very old data from a telescope called Solar Maximum Mission. It was taking data towards the sun, but it had what people have done is they've calculated the effective area of this telescope if there were any gamma ray flux received on its side shielding. And so the effective areas are very low, but you're able to look at this data and what's the word? Well, I mean, if there were a gamma ray burst observed from the supernova due to axion converting to photons, there would be some sort of excess that you would have observed in the data, but we do not see that. And people have set constraints using this data previously, as I've shown with the other ones. But what we add on to that is now we consider the conversion in stellar magnetic field and also the additional production through nucleon, Bremsstrahlung, and pion conversion. And so the limits we get
What's
from
the
that.
fractional?
Huh?
What's the fractional effective area of the solar maximum mission? Like what's their typical? If they were pointing at the supernova, what would it have been versus what it actually was?
Oh, that I'm actually not sure, because they only really quote the effective area that they expect with accounting for the side shielding, and those are like 100 centimeters squared. I would expect it would be higher, but also, yeah, I'm not sure about that one. Yeah, I haven't looked into it. It's an old telescope data, and so there's not quite a lot around, unless like digging through old papers.
Sorry, what's the signal model in the plot?
Oh, this is the signal of the background plus a signal at the time of the first neutrino signal observations from supernova 1987A. And there is essentially, this is the best fit, and it's essentially 0 in the first two energy bins, but there's like a slight, the best fit is a very small bump. I know it's hard to see, but it's like a very small axis right there. Yeah. Yeah, but the significance of that best fit signal is very low, so it's like nominally non-existent.
Now I understand how you could set a bound if that were much bigger.
Yeah, exactly. Well, if it was the best fit were much bigger with a higher significance, then we'd be like, oh, maybe we discovered something.
So
Sure.
literally
yeah.
one count, right? One or two counts.
Yeah, barely one. Yeah. So that's our fit to the data. And so this is the limit we get, once again, with 100 Gauss magnetic field, be it blue supergiant progenitor. And you can see that actually in the lower masses, we're still, the limit from the galactic magnetic field conversion is higher. The estimates were not actually exact. So you actually get a higher conversion probability with galactic magnetic fields in lower masses. But all this region above, past like 10 to the minus 9, EV is the additional conversion, the higher conversion probability that's coming from considering the stellar magnetic field. And yeah, and then there's this hashed
So
region.
your blue
Yeah.
region is for both conversions, right? So both.
Yeah.
Okay.
Yeah, we're considering joint the axion conversion in progenitor and galactic.
And you assume the galactic magnetic field is just like homogeneous, like micro Gauss.
No, not homogeneous, because we use the the more updated Unger
Models,
Farrar
okay,
models.
actually.
Yeah, and we actually integrate in
The line of
along
sight.
the line of sight.
Yeah.
Yeah, exactly.
Sorry, the black curve that's labeled previous work, I should compare that to the blue region for an ALP, not to the KSVZ.
Yeah, exactly. Yeah, you want to compare that to the.
I see. So,
So-
it's just an order 1 factor at low mass.
Yeah, exactly. It's just from the
Right.
considering the additional production mechanisms that we added on in addition to Primakov. But yeah, I guess the work is that a little bit deeper because of the additional production, but also extended further to the right because of the progenitor magnetic field effects. So yeah, this is what our limits look like from the solar maximum emission data.
There's a part,
Oh,
sorry if I really
yeah.
squint,
Yeah.
there's a part where you're weaker.
Yeah,
So
actually.
what happens there?
This is because of the different models that we're using. So this previous work used the Janssen-Farrar magnetic field model for our Milky Way. But for this model here, for our limits that show in this region, these are with the updated, I guess you could say,
Okay.
I guess,
newer work in understanding the galactic magnetic field.
so this
configuration.
happened in the LMC, right?
Yeah.
We know basically nothing about the field, like
Oh yeah,
outside
beyond
the
that,
disk.
that's true.
So like in the LMC and between the disk and the LMC, like could there potentially be a field there? That
Yeah, there could be, but we don't consider that at least in this work.
So this is just like
Yeah,
in the
progenitor,
galactic
and then
plane,
I guess a blank, and then
basically. Okay.
in the galactic.
In like this the small like couple of kiloparsec we have looking towards the LMC.
Yeah. So yeah, these are just the difference. Like if we were to use the same magnetic field model, we would just basically trace this black line up to the point where we start to win because of the stellar magnetic field. Yeah. So this next plot is just showing the limits varied based on the simulations and the magnetic field strength, and you can see that if you were to be very optimistic and say that this BSG had 10 kilogauss magnetic fields, then it would actually have a comparable limit in the low mass as well, and you would dip down further down into the parameter space. And also, just here showing the full range of simulations that we consider for the work, where it doesn't seem to vary too largely by the simulation choice that we make.
Simulation of the protoneutron.
Yeah, exactly.
Okay,
Yeah.
so that captures like the effective temperature of it, for example.
Yeah, and
So
all
you're there.
the chemical potential and all the details of the information in.
Yeah, does the axion production rate just depend on the temperature of the star?
Oh no! It depends like on the chemical potential and like the neutron,
Yeah, of course,
proton
yeah.
density, neutron
Okay,
density, all
okay.
this stuff. Yeah. So it's a lot more goes into it that is available in the simulation data. Yeah.
But it seems the key uncertainty is magnetic field.
Yeah,
progenitor.
exactly. So that's why limits are taken with the most conservative that we consider for blue supergiant magnetic fields.
Why is it so small for the simulation? Because it seemed like the temperature differences were much larger. Like the maximum temperature you reach in the 18.8 was 20 MeV or something like that, and the 20.0 was like 50. And then the production rate probably scales with temperature, like T to the 6th or something.
That's what I figured it would be.
See,
Or I guess,
Scale.
I think also it's not.
I mean, it goes like
I'm
G
sure it
to
was
the
a
4th, T
I
to
can't
the
remember
6th or
what-
something, so maybe it's somehow small.
We can look at because there's a lot of plots that I didn't add into this talk where we actually show the variation of the emission spectrum based on simulation, so maybe it might be worth looking into that. But I think what also, I guess how should it scale? But even if axions are produced higher, your G gamma gamma limit also still scales as like flux or counts to the fourth root. So even if there's like a factor of 8 difference, it would be like a factor of square root of 2
Yeah.
or so.
Sorry, where does the fourth root come from?
Oh, because the signal, so you have the production where it scales as J gamma gamma squared, And then you have the conversion, which also scales as G gamma gamma squared. And so the whole signal and counts that you would expect would scale approximately with G gamma gamma to the fourth. So you can kind of take that as like a rough estimate to see how your limits would change based on what your axion production.
Oh, okay. I
Yeah.
thought you were talking about the number density, but now
Oh,
it's
no,
G
no, no,
gamma
no,
gamma.
yeah,
Good,
yeah.
Okay, good. Yeah.
So,
Would
oh.
so you said that the radius was like 45.
Yeah, yeah,
so, like, but it also depends on the radius squared. So I mean, I guess that uncertainty is very low for the actual size of these things.
Sorry. Okay. So that's like the length scale that we use in the estimate of our conversion probability, but actually what we do in full is take the calculation of the conversion from the surface of the star out, and like the surface where that is relative to infinity doesn't seem to, it didn't affect our.
Right. Well, do you assume like just a dipole magnetic field?
Oh, yes.
But like, and over like the sun, you have much different magnetic field profile, right, for large radii, and like it actually drops, I think, less, not as sharp as a dipole. Do these like blue supergiants, are they also expected to have a different profile, like the Parker solar wind kind of stuff, or Parker?
No, because these are so compact, or like relatively compact and dense that it's easier to just approximate their magnetic field as a dipole, and it's a safe approximation. I guess once you consider, there's also another progenitor where we consider a red supergiant for future projections, where this now becomes more complicated and similar to the star, where you have to worry about like convection cells and their effect on the magnetic field structure on the surface of the red supergiant where the conversion would happen, and that gets more complicated. It's kind of like a future work that we're looking into at the moment.
Yeah.
So.
Well, imagine integrating like say it goes as instead of like 1 over r cubed, like 1 over r squared, something like that. I mean, I imagine that's a factor of a few when you integrate, and that gets squared. I mean, does that like do you know how sensitive it is to that?
We haven't looked into it, but yeah, that might be interesting to consider. But for this work, we just simply consider the dipole approximation. Yeah, to not overcomplicate. I guess if we really wanted to expand on this work, it would be like you would want to consider more realistic or physically motivated magnetic field structures and try to see how like different directions of observing it would change your sensitivity. Things like
I'm
that.
wondering if it could enhance it even more.
Yeah, that'd be nice, but not something we haven't looked into in this work. What's the time?
15 minutes.
Yeah, about 15 minutes.
Okay, so I have like a whole next half on heavy axions, but okay, so I guess I can go through this a little bit faster because the machinery is quite similar. We once again want to calculate the axion emission spectrum, calculate its lifetime, and then try to look for its decay signals in gamma ray telescopes. And this time we're actually going to consider Fermi. All right, so once again, with heavy axions, we consider a model where it couples the QED and QCD through the following operators. And this is not the axion that solves the strong CP problem, just want to emphasize that once again. And we use a benchmark of E over N equal to 8 over 3 for our results, which is like got motivated, but I won't go into the details of it. So once again...
Here for sure couldn't be the dark matter, right?
No. These have lifetimes much shorter that if you had them as dark matter, they would have decayed and nothing would be left. Okay, so same production mechanisms that we consider for the ultralight, except for the additional production mechanism with photon coalescence, where your plasma mass is, your axion mass is twice the plasma mass in the protoneutron star. And so with this, in addition to once again the supernova simulations, we get this. Where now, sorry for the inconsistency in the units here, but this is now an MEV with inverse MEV in the y-axis. Same GA gamma gamma, but I'm showing two different axion emission lines for axion mass of 1 MeV and 100 MeV for the 4 production mechanisms that I discussed previously. All right. So now with this, we're considering decay signals. So this is kind of the schematic of how the signals, how we would observe these photon signals. The axion, now that it's heavy, it's not relativistic, so it's traveling at a much slower velocity, it would travel out for a certain time until it decays into 2 photons, specifically for this case. 2 photons where one of them would have a trajectory towards Earth, where it would be observed in our gamma ray telescopes. And this would be a time-delayed signal from the event of the supernova. So like previously with the ultralight, we are observing the signals before we actually observe the photon events of the core collapse. But now this is extended after the event of the core collapse. So the lifetime is estimated in this way. There are some technical details with when the axion mass is larger than 3 times the pion mass. We also consider its decay into 3 pions, which we don't actually subsequently consider their resulting gamma ray signals. We only consider gamma ray signals from axions to 2 photons for our data analysis. But this is the schematic of how we would observe a time-delayed signal. And so this is the differential gamma ray flux equation that we use for calculating what we'd observe in gamma ray telescopes. This DNADEA, this is the axion emission that I've shown you previously in the plot. This component here with the exponential is the exponential decay of axions that have emitted from the supernova. And this last part with the Heaviside function is enforcing the decay outside the photosphere, because if your axions are too short-lived that it's actually decaying inside the envelope of your star, it won't escape to be observed in telescopes at all. So it will just get trapped, and you won't be able to distinguish that from. I don't believe you would be able to see that anymore. So that's the enforcement, and also there's also geometric constraints of like if the axion goes in some odd direction where the photon no longer is able to reach us, then that's also a constraint that's encapsulated all in that Heaviside function there. Sorry, I kind of ran through that really quickly, but is there any questions about these components?
So here, ultimately, you integrate over that whole sky, right?
Yeah.
Even on like the other side of the Earth. So, in principle, you could have something like
You
go
could,
through
but
us and then come back.
well, actually, I mean, it's only in the direction that we're.
Or is there some
Yeah,
angular
yeah.
suppression, like yeah?
Yeah, but it turns out actually it's not very that much extended when we consider like all the other, like for supernova 1987A, I don't think we actually see any. Like this is a very exaggerated schematic. It's mostly all towards
it's mostly
Earth and then
towards
yeah,
gamma, right,
exactly.
when you do the conversion.
And then decay. Yeah.
Okay.
So.
Okay, so there probably won't be
Oh
many
no.
photons
Yeah.
coming from the
I mean,
outside.
also if it's like gone past Earth, you would have the probability of that decay the photon from that decay coming back towards Earth is also very low, right? So, yeah. Unless it's very, very non-relativistic, making it very heavy, then it's also too short-lived to actually travel that far. Yeah, there's all these parts that are playing around in this and sort of tied into this function here. Yeah. Yeah.
So why is it E gamma over MA and not the reciprocal? Like is that the Lorentz factor?
Oh.
It shouldn't be enhanced. Like lifetime should be long for large energies, right?
Lifetime should be long. Wait, sorry. Why would the lifetime be long for large energies?
It's Lorentz, just time dilation, right?
Oh, but these axions are moving in a very non-relativistic speed because they're very heavy. They're like MeV, right? And so it's just.
Right, but doesn't depend on the energy.
The temperature is 20 MeV, so it could be some of them are semi-relativistic.
Yeah.
Right, like what is the MA over 2E gamma factor coming from?
I'm not sure if I remember off the top of my head. It's been a while. I'd have to sit down and kind of remind myself of it, but.
Okay. And sorry, this is decay, so not.
Yeah.
Yeah.
So in that, I guess in principle, that signal could be pretty isotropic, right?
Around
as long as they can make it
yeah,
far
it
enough
could be
out.
like a fuzz of signal around the
Yeah.
supernova target. Yeah. But that would also, well, I mean, we say fuzz, but it's still very like centered, and also.
It
I
just
don't
depends on the
know.
lifetime, right? Like if the lifetime is very long, I don't know what exact lifetimes you're looking at, but it could be very large.
Oh yeah. It could be like years, tens of years.
How far would they? It's like.
10 years and they're moving at the speed of light, it would be a couple parsec.
Right, but they're probably
Over 50
sub-relativistic,
kiloparsecs.
right?
Huh?
They're not quite relativistic.
But let's say
yeah.
the maximum, right?
Yeah.
It would be 3 over 10 years. It would be 3 parsec
Sure,
over
sure.
50 kiloparsec, which is
Still pretty.
probably still smaller than Fermi's angular resolution.
Mhm. Yeah, yeah. I mean, there is one target that we consider additionally. I guess maybe it's on the next slide. Oh yeah, okay. So there are actually additional targets that we consider in addition to Supernova 1987A. This one specifically, it's Cassiopeia A, which people estimate to have gone off at around 1674. And this one has it has the most extended, but it's still like only a few degrees off of the target. So yeah, with 1987A, it would be like almost within the angular resolution for me. Yeah. So these are the additional targets we consider for this heavy axion signal search, where once again Cassiopeia A, which is the closest and went off at 1674. We also consider these two newer ones, where these are further away, so we don't. Oh, I guess for all these three, we don't know exactly the time when the core collapse occurred, so it's hard to, pinpoint when to pinpoint that exact moment where the data would be available. So there's a bit of an analysis variation we do in how much time we take before the actual photon signal observation of the supernova for these cases.
Sorry, why don't you know them for 2023 and 24?
Well, we don't know exactly when the core collapse occurred, right? Because the time of our photon signal observations doesn't correlate with the core initial first seconds, right? We'd have to have a neutrino signal, but we aren't able to observe them for these far distances. Yeah. And obviously for this, we didn't have the detector at the time. So, taking that, so for this...
Sorry, how do we know that the Cassiopeia one is a core collapse?
I believe this one, I think people specifically have observed the remnant for it. Since it's been so long and the outer envelope has dissipated enough to be able to see what's remaining of the supernova. Yeah. So, yeah, it's old enough that we know what's remaining from that event. And so for this work, we take the data from Fermi for specifically for Supernova 1987A and Cassiopeia A. We take the full archive of, I guess now, at the time, 16 years of data. And for the newer ones, 2023 and 2024, we specifically look at different time windows. There is this label V1, and this is related to what different ranges of time for data we use. And with this analysis, we get this limit for the 4 targets we considered.
Wait, can you just go back?
Yeah.
It looks like there's like 1 or 2 data points. Whoa, okay. No, for the black bars. Okay, sorry. No, you can kind of see deviates from flat. I was just, sorry. This looks good.
Oh, okay. I mean, if you're wondering about the 1987A result, there is 2 sigma preference for signal.
Yeah, I
and
can kind of see that.
Yeah, that's what you see here. So maybe it could be, but the unfortunate thing is that the best fit signal for mass versus J gamma gamma is like a lifetime of 10 years, and Fermi only started like 20 years, I guess, after the time of 1987A. So it's hard. You'd have to do a very precise timing analysis to resolve this, but we haven't done that due to complications with Fermi. But yeah, so this is the limit plot. There are some weird shapes for the limits for the older ones, and these are the geometric restrictions that I mentioned previously, where I guess if it's too short-lived, it would have decayed before the time that Fermi started taking data towards the target, and also if it's too light, it would have just whizzed past us. No, sorry, but yeah, there are geometric constraints that it's harder to. It doesn't have the exact same shape that extends towards the lower masses as the newer supernova targets.
What does the freeze-in thing mean?
Oh, this is just from another work that I think this is the irreducible axion background work that Kevin, Nick, and Nadal put out a while back.
It's like if you reheat the minimal temperature of 10 MeV, you still produce some cosmological axion background, and then that can decay to X-ray photons.
Okay.
So yeah, once again. So okay, that concludes the heavy axion part, and I know I'm running low on time. How many? 3 minutes?
Okay. Yeah.
But-
Officially, maybe in a minute or two, because we talked a
Okay.
lot, but yeah, we should finish pretty soon.
Okay, I'll just kind of go through this really quickly. There's a couple of progenitors that we consider with projections, potentially if Fermi were to directly observe the supernova event at the time of core collapse. And it seemed, okay, for this, we take a 1 kilogauss blue supergiant located at 10 kiloparsec away so that we would be able to observe the neutrino signal from the core collapse. And so actually you see that it's kind of hard to see in this projector, but the KSVZ and DFSZ actually go down into the regions of interest for QCD axion at above 10 to the minus 4, 5 times 10 to the minus 4 or so. And so this was really exciting. We also consider, so this varies based on, of course, the magnetic field strength and the simulations you consider, but still seems to show promising prospects for looking into QCD axion at above 10 to the minus 4 eV. Additionally, there is also this other different progenitor that we can look for.
Sorry, this is a 10
projections.
kiloparsec progenitor, so once every 100-year event.
Yeah,
right?
exactly. But I don't think people. So the thing is, people say that this hasn't happened yet, and we're long overdue. Is what I've been hearing a lot. People quote. So that's why we're pushing essentially for this future gamma ray.
That's not how Poisson
Yeah.
Yeah, but and this is something we're playing. This is our agenda.
Don't try to trick us.
But so this seems to show promising results, but additionally, the more common progenitor for core collapse is actually a red supergiant. So this is kind of like an image that I tried to scale pixel-wise to what the size difference would be compared to a red supergiant and a blue supergiant. Although it's a more common progenitor, it has much weaker magnetic field strength. It's like Gauss at most, I think. But like we mentioned previously, there's like these complicated structure with convection cells and things like that we have to consider more in detail. But for this projection that I'm about to show, we just do a simple estimate of the field strengths with equipartition theorem shown here. And so this is the projection we seem to get with the red supergiant. Kind of close, but I think there could be potentially some improvements of the conversion rates with different magnetic fields, more sophisticated simulation results we use for red supergiants. So this also seems promising. It's getting very close
Sorry,
to
I'm
the
ignorant.
region of interest.
It's the red supergiant plus the blue supergiant rate that's like once per 100 years.
I think
right.
so.
So what's like the relative fraction? Is it 50-50 or?
No, I think it's mostly red supergiant.
So the blue supergiant is
It's
maybe
rare.
once per 1,000 years, or,
Yeah,
or what's that? What's the?
I'm not sure.
Blue supergiant 10 kilopart. Is that
But
10% of the supernova? And that'd be once per 1,000 years, or is it even less than 10%?
I don't think the details of the modeling of
I see. It's
really
pretty
massive stars are that
So,
that precise.
but still with red supergiants, I would say that the ELP also region of interest seems really, really promising. So, but then I guess, this is also once again preliminary, so we are trying to get more sophisticated red supergiant simulations to understand the magnetic field structures. This is more far-fetched. We're going to wilder ideas. So now you can also maybe consider a neutron star merger event to search for these axion to photon signals. And this is a really, really, really crude estimate. I just want to put that out there. This is an estimate where we took the heaviest supernova simulations to kind of see what the internal properties would be like, and took that with a strong magnetic field and did the calculations. So this is, I would take this with a lot of salt and don't take it too seriously, but it still shows that, kind of demonstrates the fact that if you have a stronger magnetic field, you're able to reach to higher masses in your sensitivity for the conversion. But there's once again still simulations that could be done to understand better what the magnetic field structure would be and things like that. And also the thing with neutron star mergers is like with supernova you have the neutrino signals to pinpoint the moment of the core collapse event. With neutron star merger events, you would have the gravitational wave signatures to pinpoint that moment of where like the events get, well, I guess the merger event happens. So that's why we're considering this as another candidate for future projections.
I have a question on this.
Yeah.
Why, at high masses, why do the constraints fall off like
Oh,
exponentially or so much faster?
this
than-
is because of the strong magnetic field. I'm forgetting, there was this, yeah, the conversion probability doesn't scale just as the, what is it, G inverse MA, is that what it is? Or MA?
Like
Yeah.
inverse MA squared?
Yeah,
So
yeah,
it's
yeah.
like exponential or something?
Yeah, there's more of what's the term? I remember the initial, the EH term starts to make it such that the conversion starts to become much more ineffective very quickly because of the,
Like that formula that
Like,
M
I got- yeah,
squared
show the
over,
formula,
over
yeah.
2 times L, that was really probably an oscillation rate
Yeah,
times
exactly.
the length. And so really in the oscillation rate, you have all the masses that enter. So before there was really a photon thermal mass, which was small, so you neglected it.
Yep.
And now you have the
But now it's
Euler-Heisenberg
just
mass.
Yeah,
some
exactly.
structure of the magnetic field that gives you.
Yeah, so it's really, you need MA squared plus M Euler-Heisenberg
Yeah.
squared
Yeah.
in there. And M Euler-Heisenberg starts beating out, I'm guessing.
exactly,
MA
yeah,
here.
that's right.
So you're out of time.
Oh no. Okay, let me just flash this idea that we have that with some prototyping we're going on at with people at Space Science Labs at Berkeley. I don't have any, there's a lot of preliminary work going on that seems to make this more promising than when I initially had this in the paper. So I'd be happy to hear any particle physics ideas that people might be interested in probing with an MEV to GeV telescope with transients or any short-lived signal that you might benefit from having a 24/7 full sky survey. So just wanted to put that out there because we're gathering ideas to make the science of it more broad. And so yeah, this is our, I guess, the final plot, the summary of the limits in the ultralight and the heavy axion. So thank you very much. Yeah, so I guess
We had a lot
questions?
of questions during, but any more final questions?
Yeah.
I had a question about the neutron star merger one.
Yeah.
You said you were looking at like a fiducial 30 megaparsecs, so
Yeah,
like relatively
yeah.
far away.
Mhm.
Is there any way you could win out by probing larger volumes? Like the number with Rev goes like as a volume, R
Mhm.
cubed, but you know you wrote something earlier about how your probabilities or your flux decreases with distance.
Mhm.
Like can you ever win out with probing like a much larger volume? Because like I mean,
I don't know. I don't think so. I believe your limit would just get weaker, even if you look at more. Okay,
we
maybe.
have more of them, right? R cubed.
Yeah, that's true. But
Right.
I mean, even with I guess maybe if you do a joint analysis of all the merger events that you observe and set a joint constraint, it would be slightly stronger, but still, I don't know if it would win over what you lose in distance. I think that would remain in the details of the analysis done, yeah. So it's hard to say. Yeah, any other questions?
Let's think. Yeah.